many, the load on the server gets so high that we can't tell when we crash it or not, because it takes so long to respond to requests. But by doing this, we don't need to produce any more infinite loops. We fill up the buffer that we've already guessed up till the one we're guessing with these CD instructions. And what a CD is an interrupt. And when the parameter in an interrupt is CD, that's guaranteed to crash a user process, because user processes aren't allowed to run the interrupt instruction with that parameter. So no matter where we fall in that zone, we're guaranteed to cause a crash. And then for the position that we're guessing, we try to guess a near jump. We try to guess the short jump that jumps to the location where we put the near jump that will continue normal execution. So if we guess correctly with this setup, the program will continue executing normally. We'll be able to observe that remotely. If we guess incorrectly, it's guaranteed to crash. Okay? And the number of guesses we need is really low. Right? We need, on average, 15.5 expected guesses to find the first infinite loop. And then we need, on average, 8 guesses after that to figure out what the correct mask is. So we need less than 24 guesses per byte to find the instruction key. OK, so we did some experiments with this using the RISE implementation of ISR that was kindly provided by Stephanie Forrest and her student. The first thing we discovered was that memory space randomization actually works. That we were running these experiments on a Fedora machine. And Fedora, by default, does do memory address randomization. So this meant we couldn't find the stack to inject the attack. We could use the Dan Bonnet's group attack to break the memory address randomization. In this case, it was easier to just turn it off since we control both machines. But the combined effect of the two certainly is stronger than just having one. The next thing we needed to do involved one of the other requirements not actually being true for RISE. So one of the requirements for the attack is that we can run the attack lots of times, cause the process to crash without the randomization key changing. And the way RISE does randomization is it has a cache of the randomization keys for each location. And that cache gets filled up as different segments of memory are loaded. And the problem is when you fork a process, if the keys for that location haven't been used yet, so they'll share the keys for the locations that were already touched, but they won't share the keys after that. So if the place where you're injecting the code is a location that wasn't read before the process forked, then the key there might be different from the key that another process has, another child has. So we modified RISE to avoid that complexity. And that meant that we read the whole cache of key bytes before the process is forked. And other proposed ISR implementations don't work that way. It's certainly a sign that this would be a useful thing to actually build into an ISR design to make sure that every time a process forks, it has its own keys. If you're doing the randomization at compile time, like the proposed Columbia implementation does, you wouldn't be able to do this. All the processes would have the same key. And we find that we're able to obtain the correct key almost all the time. The reason we can't always obtain the correct key is that sometimes the guesses that we want to make to distinguish between possibly correct guesses would require us to put a null on the stack. And because we're doing the attack by injecting bytes on the stack, we can't inject a null, because that would end the string where we're attacking. We couldn't have anything beyond that. So we're not able to make the guess that we want to make, and we're left with more than one possible key at some location. But most of the time, we don't run into that situation. So here's the number of attempts that are required to obtain keys of different sizes. We'll note that this is a log scale, so we're obtaining large keys. To obtain the first 2 bytes takes a little over 4,000 attempts. This makes sense. We need 2 to the 12 attempts to try all the guesses, and we need some additional attempts to distinguish possibly correct guesses. So that's why it's a little above 2 to the 12. And to get 4,096 bytes takes a bit over 100,000 attempts. So the attempts per key starts to decrease. Right? So as we learn more information, we can start using the more efficient attack. We need a lot of attempts to get the first 2 bytes. And once we're getting long keys, it's down to less than 24 attempts per byte. Yes?
It seems that the returns instruction will be more effective with saying the trap, based on the figure.
Yeah, OK, so the return attack, we're guessing a 1-byte instruction. So let me go back one slide. So we can see with the return attack, we can get 1 key byte at a time. We can get the first key byte with just 256 maximum guesses. So it is much faster. The problem is we can't always use the return attack because it only works on vulnerabilities where the server does something noticeable quickly after the vulnerability. Otherwise, the process is going to crash. But if we are lucky enough, or the attacker's lucky enough, to find a vulnerability like that, then the attack works much more quickly. Thank you for pointing that out. OK. So what really matters to the attacker is not the number of attempts, but how long it takes. And so the time it takes is on this graph. And we're able to get the 4-byte key in just under 3.5 minutes. And getting 4,096 bytes in 48 minutes. So does that seem good enough? How would we decide if that's good enough? So do we know how many bytes we need? Well, we know if the key is repeated, if we get the whole key, we've got enough. But if the key is not repeated, we need to figure out how many bytes we need. So that depends on what we want to inject. And if we just want to compromise one server, then we just need to break enough key bytes to inject the malicious code. And malicious code can be pretty small. The Sapphire worm was only 376 bytes. So we can do a lot of damage with a few key bytes. But if ISR is successful, then we won't just be attacking one machine. We'll be attacking a network of machines that are all protected with ISR. So that means not only do we have to have the malicious payload, we have to have all the code that we use to do the key breaking. And that's pretty complicated, right? It has to manage all this guessing, has to keep track of things. The implementation we have is 34,000 bytes long. I assume if someone worked really hard, they could get that down to maybe 1/4 the size, but not a lot smaller than that. And so to get enough key bytes to hold that code, well, we need to crash the server almost 1 million times. Most sysadmins should notice when their server processes crash 1 million times. So this is probably not good enough. We need to think of some way to make it better. And the way to make it better is maybe to think of, well, we can, instead of being really clever and making the code smaller, we can find a way to inject code without needing to break all the key bytes. So if we're able to break enough key bytes to inject a virtual machine, well, then we don't need to break any more. We can run our attack code within the VM. So VMs are pretty big, right? VMware is 3.5 megabytes. We're not going to inject enough bytes to hold that. There are smaller VMs. Java is a bit over 100,000 bytes, but still bigger than our attack code. At least in theory, we've seen real small examples of universal machines. Minsky designed a Turing machine that only needed 7 states and 4 colors. But even injecting that would require several thousand bytes probably. And it would be hard to write malicious programs that run on it. So we can do better than that, though, because we don't need to build a complete standalone virtual machine. We can take advantage of what the Intel x86 processor already gives us. And it turns out that we can write a micro VM big enough, powerful enough to run any worm that we want with just 100 bytes of code. So I'll show you that code. There it is, just 100 bytes. And it's actually only 76 bytes of code and 26 bytes of no-ops. So I won't leave this up long enough for you to actually read it all, other than to get across the point that it is really small. Right? The entire VM fits on this one slide with reasonable size fonts. And here's what it does. So the goal is to be able to run the attack code in locations where we know the key. So we need to have some location where we can take a block of attack code and execute it with known key bytes. And that's what the 22-byte worm execution buffer is. The reason it's 22 bytes